Hello and welcome to my presentation for my final project. Today I'm going to be talking about the Fairy GodModel. For my final project, I decided to develop a time-aware machine learning model that predicts Walt Disney World attraction wait times using historical queue data along with factors like weather, holidays, seasons, and school schedules. This model is an attraction recommender that suggests optimal ride times to theme park guests. The model effectively recommends which attractions should you ride now or when should you ride your desired attraction. Now let me switch over to my Jupyter notebook so that you can follow along. At the top here, I just have some text related to the product description. As I stated, I will be developing a time-aware machine learning model to predict Walt Disney World attraction wait times. My models will be evaluated by using a time-aware trained test split, meaning that the model will be trained on older dates and tested on newer dates. This should allow the model to capture seasonality and trends without any data leakage. And my baselines will include a very simple baseline where I'm just predicting the average wait time for the attraction, and then also a simple linear regression that just uses a handful of features. And I will talk more about what features are available in my data in just a moment. Overall model performance will be assessed by computing the root mean square error, or RMSE, on the held out test data. This provides a measure of how far the predictions deviate from actual wait times and especially penalizes large errors. In addition to an overall score, RMSE will also be broken down by attraction, hour of the day, and season in order to better understand the nuances of how each model performs. Now let's get into the exploratory analysis. This dataset is provided by touringplans.com, which is a third-party company that specializes in saving people time and money on their Walt Disney World vacations. For 15 plus years, this company has collected wait time data for Walt Disney World attractions, as well as other metadata that may influence crowds. This additional metadata includes things like school session schedules for major districts in the United States, weather information, and special event information. Touring Plans, the company, uses this information to publish a crowd calendar that provides a predicted daily crowd level rating out of 10, 1 being very low crowds, 10 being very high crowds. And as the company name suggests, they also offer customizable touring plans in which they use their own machine learning models to tell their customers which order they should visit Walt Disney World attractions so that they spend the least amount of time waiting in line. The specific dataset that I used is provided by Touring Plans for educational purposes and can be found at the link in the notebook. It consisted of wait time data for 14 attractions from 2015 to 2021, with at least 3 data points per attraction per hour during park operating hours. Additionally, there is a metadata.csv that contains contextual information for each day from January 1st, 2015 to August 31st, 2021. This metadata includes information such as the day of the week, if it was a holiday, the weather that day, the percentage of US students in school, as well as other metadata, which we will get into later in the notebook. I've also included a link to the raw data in a Google Drive share folder in case you'd like to take a look. Before we get into my work, I'll discuss some related work. So for the first question, how has this dataset or similar datasets been used before? As mentioned previously, Touring Plans uses this data to train their own machine learning models to predict both crowd levels and to create customized touring plans that minimize time waiting in line. Additionally, I found an article published in the University of Texas San Antonio's Journal of Undergraduate Research that uses this data, as well as a master's thesis from California State Polytechnic University that uses this data. How has this prior work approached the same or similar tasks? I could not find any public information about Touring Plans as models. However, the undergraduate paper used multiple linear regression models with dummy variables for season, which included 17 season categories, and the attraction within each park. They used only these 2 features to estimate the expected wait time for any ride or season combination. Now, the master's thesis had 3 goals. The first goal was to identify which variables, season, weather, weekday, holiday, etc., from the metadata.csv best explain the daily mean wait times for 6 attractions from 2015 to 2019. Their second goal was to compare pre-pandemic wait time patterns to those observed in 2020 and 2021 to try to quantify the impact that COVID-19 had on wait times. And then finally, they built a statistical regression model to predict what 2020 wait times would have been under non-pandemic conditions and compare that to what the values actually were during the pandemic. So how does my results match or differ from what has been reported in related work? Well, the work that I'll be showing that I did is similar, and we all used some type of regression. The tasks were different enough that I had no direct results to compare to. Now let's get into my data. 2.A describes how I loaded and processed the data. This first section of code mounts to a Google Drive that contains the files from touring plans as well as loads the relevant libraries that will be used later. Then this next section of code reads in the CSVs for each attraction, of which I had 14 CSVs, and it merges them together and appends the attraction name next to each line of the data. The resultant pandas data frame is shown here, where we have date time, wait times, and the attraction name for all of the data. And then this resulted in over 3 million rows of data, 3 million ride, date, wait time combinations. The next notebook is just making sure that these columns are converted to the right data types. And then finally, I looked at the minimum and maximum date and time for each attraction. Here, I noticed that all of the data ends on December 28, 2021. But while most of the data begins on January 1st, 2015, there are a couple of attractions that start in 2018 and 2017. And this is just when these attractions happen to open. Considering this date range, I decided that I was going to drop the COVID years as they were just too anomalous to include in my prediction, which ultimately meant that I decided I would train on 2015 to 2018 and then predict on the 2019 data. So the first thing I did here was trim all of the data to end at December 30th, 2019. Then I extracted some useful information from the timestamps, and my final data frame can be seen here. I noticed in the data description for this data set that it was reported that a wait time of negative 999 would be posted whenever the ride was down. The data description also mentioned that there was potentially outlier data. And so because of that, I decided to drop the negative 999 wait times and also drop any wait times that were larger than 420 minutes or less than 0, because this represents a realistic wait time range. So that's attraction and wait time data. Next, I moved on to loading and processing the metadata.csv. So I loaded in a CSV file, and then I decided out of the over 150 columns in the data that I would focus on just the feature columns listed here. So I basically read through the description of the data and narrowed it down to pick what I thought was most relevant, just to keep the problem and my model sizes small enough so that they wouldn't be too unwieldy or running forever. The next bit of code just cleans up this data, so fills in nulls, makes sure that the types are all in alignment. And then I also noticed that these in-session enrollment percentages were actually a string with a number and a percent. So I used this code to strip out the percent sign and then convert that percent to a decimal fraction. Here's a representation of just the finished, cleaned metadata data frame. So you can see all of my columns here, and then 2079 non-null values. This is an example of what you'd see in this metadata data frame. So you can see, for example, for January 1st, 2015, it's the 5th day of the week, and 00 for day of the year, week of the year, 1 for month of the year. It's the Christmas peak season. It is a holiday, and then all of this other data here listing out park hours and things like that. I took this metadata and merged it with my wait time data, which gave me essentially this data frame. So now we have date time, the wait time, the attraction, the hour, and the minute of that wait time, and then all of the metadata associated with that particular day that came from the metadata CSV. And this is what I'll be using to train and then test my model. So I'll be using some or all of these different features to predict this wait time. So I used this data frame. This is just the same data frame, but after I finished that analysis, I saved it as a Parquet file so that I could easily reload that file later without having to rerun the whole notebook. And that's just what this first bit of code under 2B is doing. And then I decided to make some exploratory charts. So first thing I did was just aggregate some statistics about these wait times that are displayed here in this table. So for each attraction, I list the start and end date of the data, how many different wait time we have. That's the row count here, how many different data points we have for that particular attraction during that date range, what the minimum and maximum waits were during the data time frame, and then for each year, what the average wait time was during that year. The next bit of code here, 2C, is just exploratory plot. So I use Matplotlib and Seaborn to just make a box plot of the wait times by attraction, and then sorted it by lowest median wait time to highest median wait time. And understandably, the highest median wait time is a very popular e-ticket attraction, the Avatar Flight of Passage ride at Animal Kingdom. And the lowest wait time is what you might consider to be a filler attraction, Spaceship Earth. But interestingly, too, there's quite a spread on almost all of these rides. So there's times probably early in the morning, late at night, where we're getting close to zero for the wait time. But then there are other times, middle of the day on a peak holiday, probably where we're getting really high wait times. The next plot that I made here is just a scatter plot of posted wait times over time. This is similar to what Professor did in one of the lectures. So I have the timestamp on the x-axis here, and then I have what that posted wait time was. And you can see that when I plot all of the data like this, it's really overplotted, and you can't really see any trends. But then I did apply a moving average to the data, and then now you can see the daily means versus the 7-day moving average. And from what was quite a busy scatter plot, you can now kind of tease out the weekly, seasonal, and sort of yearly variation in the wait times. So you can see each tick here is a 3-month period. You can see that there's seems to be a time in each month where you have low wait times, and then times where you have high wait times. And then overall, we see a spike in the wait times in around 2017, 2018, which is when those newer attractions come in and enter the data set, and they push this whole wait time data higher. Just for fun comparison, I also included moving average of what could be considered an e-ticket attraction, Seven Dwarfs Mine Train, versus filler attraction, Spaceship Earth. And you can see it almost looks like I've shifted the data, even though I haven't. The e-ticket attraction, or the more popular attraction, kind of starts high and remains high, even though it does have these seasonal or these sort of daily variations. Trying to start looking at what metadata features might impact the wait times. I plotted the average wait time by day of the week, and interestingly, they were all pretty close to one another, with Monday actually having slightly higher wait times. I also wanted to look for the popular e-ticket Flight of Passage attraction, if there was a visible difference between holidays and non-holidays. And I actually don't really see a difference. In fact, some of the higher wait times here were on a non-holiday, which I actually assumed to be the opening days for this attraction when it was brand new. That's what I expect these dates to have been. So after looking at the data through these exploratory charts and plots, I moved on to my models, starting with the baseline models. The goal of my models will be to predict wait times. And so, in order to format this as a machine learning problem, all of these columns in here are my features or my inputs to the model, with the exception being the posted wait time here, which for the training data, that will be what I'm trying to minimize the error on. And then for the test data, I'll be trying to predict that and compare to actual values to get my RMSE. Just a reminder, my basic models are going to be predicting the average as well as a simple linear regression. And then my more sophisticated models will be a cat boost regressor and a linear regression. In all cases, I'm trying to predict a continuous numeric value, so it makes sense to use some form of regression for this. First thing I did was split the data into training and test. So between 2015 and 2018, that's my training data, and 2019 will be my test data. My first model here is just predicting the average wait time. So it's really simple code, just grouping by attraction and calculating the average and then predicting that for each row of the 2019 test data set. However, that's an extremely simplistic model, and we could see in the plots that there's seasonal, daily, monthly variations to the data. So understandably, the RMSE for this model ended up being very high at over 31 minutes. And I'll have a plot later that compares the RMSE for all these models in a little bit better of a visualization. My next baseline model was to use linear regression with just a few select features. So I basically just took the time features and used that to try to predict what the attraction wait time would be based on given attraction and these day features. Again, both of these models, the advantage is that they're really simple, but unfortunately, they just didn't perform well. In fact, this linear regression model performed even worse than just predicting average with an RMSE of over 41. So the first more sophisticated model that I chose was a cat boost regressor. This is a model that I learned about in another class, and it's essentially a gradient boosted decision tree that can handle both numeric and categorical features. So I could feed it both categorical features like the attraction name and the season name, as well as all of my numeric features like the temperatures, the hours, the percents of schools and sessions, stuff like that. It's essentially a model that makes an ensemble of decision trees where each one is trying to improve on the previous tree and reduce the RMSE. Overall, it's more complicated to set up, and it also took much, much longer to run than any of my other models. It took about 30 to 40 minutes to run. And surprisingly, the RMSE is better, but not good enough. Like an RMSE of 26 minutes on wait times where we were getting averages around 50 minutes is really high. However, a fun thing that I was able to get from this model, because I was using so many of the features, was this plot of feature importance, which is kind of interesting to see that things like attraction and the time of day and the year seem to have the highest impact on the wait times, where if I scroll down, things like whether or not there were events going on at different parks seem to make almost no impact on the wait times. So that was interesting to see. So for my last model, I decided to go back to linear regression, but this time incorporate the temporal features that we learned about near the end of the class. Because thinking about it, I figured that one of the best predictors of wait time currently is probably what the most recent wait time data points are. So I used this code to make these lag and roll factors that are calculating and adding in a feature for what the wait times looked like in the previous hour, in the previous day, and the previous 15-minute interval. And I added those as features along with the day, year, week, month information into the linear regression. So this is a lot of the original linear regression in the baseline, but now with these added lag features. And unsurprisingly, this was my best performing model with an RMSE of only 9 minutes. And so if I scroll down to how I evaluated and made my conclusions, I used this code, Seaborn and Matplotlib, to plot up all those RMSEs that I just calculated to get these plots. So you can see here overall RSME on the whole test data, the linear regression was the worst and the time aware linear regression was the best. If I look at it by attraction, you can also see that while there is variation attraction to attraction, the time aware linear regression was the clear winner. For hour of the day, again, similar story. Some models performed slightly better. The cat boost actually did pretty well in some hours of the day, but again, time aware linear regression dominated. And the same is true for the month. So just by comparing the RMSEs, I was able to determine that the time aware linear regression model was probably the best out of everything that I tested. The only potential issue with this model is that it does require you to have all of the data leading up to the current point in time that you're trying to predict. So it'll be, yes, less useful in predicting wait times far out into the future. In that case, further refining some of the other models like cat boost regressor would probably be the way to go. But overall, this was a really interesting project and made me even more curious to see if I can figure out what models the Turing Plans company actually uses in their software. And I hope you enjoyed listening to my project. Thank you.